can combine the parallels,
Which parallel?
the impedance.
Well, tell me,
Uh,
tell me how I would do this.
R3 and C2 are in parallel.
Well, these three are in parallel,
Yeah.
right? So Z equivalent is equal to the product over, you can't use the product over the sum. Remember, you can't do that, right? So you have to get Z equivalent, right, for ZL, ZC2, and R3. And it's not the product over the sum. That only works for two. So it's remember it's 1 over Z equivalent, right? Equals 1 over ZL plus 1 over ZC2 plus 1 over R3. So now you've got Z equivalent, right? So now we can redraw our circuit. So now you have plus and minus, E in, you have R1, you have R2, and you have, this is what, Z equivalent, and this is E out, right? So then if we label, oh, I'm sorry, well, I forgot this one, yeah, gotcha. And this we have, this is Z C1. Now, these two are in series because, why? Because we assume that I out equals 0. There's no loading of the circuit. So these two are in series. Yeah, but you see, but why can't you combine them in series?
You'll lose E out.
Yeah, right. You'll lose the out. So that doesn't work. But you recognize if you call this, define this as E1, then E1, then the circuit that you have then is E1 into R2, right? Into Z equivalent, and this is ground, and this is E out. So now you have a voltage divider, right?
That also goes into C1, no? Like,
What?
as a separate branch?
No, E1 is here.
Oh, okay, we're not, okay.
I'm using this node here. Yeah, it does, but I'm not analyzing that portion of the circuit. This voltage is on the other side of this voltage. So I'm just, these two form a voltage divider. If I call this E1. So then you see that, so then E out is equal to E1 times what? Z equivalent over R2 plus Z equivalent, right? So from this, you know the relationship between E1 and E0. So now you come over here, so now you know E1, and you know ZC1, so now you can draw your circuit diagram again. So now you have what? You have R1, and then you have ZC1, God bless you, and this is E1, and this is ground. So this is E in. So you have E in, and then you have a resistor, and E1 is your output voltage, which is what you want to find. So this is another voltage divider. So in other words, so you see that, so E in, so you see that, I'll write it over here. So E1 is equal to E in times what? ZC1 over R1 plus ZC1. So now you know the relationship between E1 and E in. You know the relationship between E1 and E out. So then you can solve for the relationship between E out and E in. Any other way to do this, I think, is going to be much longer and much more involved. And then out of this, you get a third order ordinary differential equation. So again, the impedance technique is a very, very powerful technique, and it makes the math much simpler, especially if you don't carry through combining things in series and parallel, and just use equivalent impedances and just carry that work through, and then do the detailed work once you've got the whole scheme laid out. Okay? You have any questions on this?
Could you go back to the previous page and correct that something?
excuse me, sure, what, this one? Sure,
Yes. Thank you.
oh, okay,
Thank you.
you're welcome. All right, so that's that. So this one, can you, I decided that, I don't want you to struggle with this, just take one and pass it around, please. So this problem makes use of the fact that most systems are combinations of low water systems. And the low water systems that we know of are an integrator, and then a first order system with the time constant in the denominator, and then a numerator term. So these are three expressions that can be combined to represent complicated systems. There's also a differentiator, an S. There's also second order terms that we could use, but we didn't cover those, and so this is not, won't be part of this solution to the problem. So you have to then understand, since we're talking about frequency response, what the Bode plots of each one of these look like. So what's the Bode plot of 1 over S? Well, you could go into MATLAB and do that, and what you're going to find is that the Bode plot for 1 over S, if this is 0 dB, and let's say this frequency omega is 1, then 1 over S goes through that point with a slope of minus 20 dB per decade. All right, that's 1 over S. So it has to go through this point, which is 0 dB, at a frequency of 1 radian per second at minus 20 dB per decade. That's 1 over S. And the phase angle in degrees is constant at minus 90 degrees. So it's minus 90 degrees for all frequencies. So an integrator gives you phase lag or time delay at all frequencies, minus 90 degrees. Okay, so that's 1 over S. So we got to keep that in mind. If you look at what is K over tau S plus 1? Well, we know what that is. So that's, if this is omega, then this is, let's say, 1 over tau. Then if this represents K, then what does our Bode plot look like? Well, asymptotically, it's flat out to 1 over tau and breaks down at minus 20 dB per decade. Per decade is a 10 to 1 frequency change. And what does the phase angle plot look like? Well, the phase angle starts at 0 degrees, goes to minus 90 degrees, is minus 45 degrees at the break point. So what does this look like? This is 1 over tau. It looks like this. This is 1 over tau. So now we know what the phase angle and the amplitude plot looks like for K over tau S plus 1. What does it look like for just K times tau S plus 1 over 1? Well, it looks the same as this, except it's just flipped. It's just the mirror image, meaning that the magnitude plot looks like this, it goes like this and then up, and the phase angle plot goes from 0 to 90. So it starts at 0, goes to plus 90, and then goes to plus 45 degrees at the break point, 1 over tau. So in other words, this is the exact, it's not the mirror image, it's the what? It's the reflection about the frequency axis. Just flip it over. This is going up. Minus 90 becomes plus 90, minus 45 becomes plus 45. And so that's what the Bode plot for that looks like. We'll just type it into MATLAB and ask for the Bode plot, and you'll see it. Okay, so how do we use this information to get the Bode plot for this expression, for this? So where would this Bodhi pod come from? Well, it would come from a dynamic signal analyzer, or it could come from even manual Bodhi podding. But this is frequency response, so it's magnitude in dB versus frequency, phase angle versus frequency. And we want to get an expression for the transfer function for this Bodhi pod. And you say, well, how the hell can I do that? Well, you do it by using the idea of asymptotic lines. So if you look at what I've done here, so you see what I've done is if you look at the plot underneath this, and in your solution, you have to supply something like this to show how you did this. So in other words, so the only thing that can give me a non-zero slope at low frequency is a 1 over s, or a 1 over s squared, or s squared. But everything else is flat to the break point, and then it breaks down or up. So what is 1 over s? Well, 1 over s would be this. And you can see it goes through this point here, which is frequency of 1 at 0 dB. So this is 1 over s. So this is minus 20 dB per decade. How do I know that? Because this is 2 decades, right? This is 2 decades, and this looks like it's about 40 dB. So this is going 40 dB in 2 decades. So it's minus 20 dB per decade. Now, the whole idea behind Bodhi plotting on logarithmic scales is that multiplication becomes addition, division becomes subtraction when we use logs. So the fact that this is a semi-log plot, dB has already been converted. So your phase versus log, dB versus log. The fact that it's a semi-log plot means that multiplication becomes addition and division becomes subtraction. So my first thing is if I just add what? How much do I need to add to bring this up to this level? Well, you have to ask yourself the question, what's the difference between this point and this point? Well, this looks like it's about what, 80? And this looks like it's about what, 20? Or 120? So the difference between 80 and 120 is 40 dB. And what's 40 dB in numbers? What's 20 dB in numbers? 10. What's 100 dB? What's 40 dB in numbers? 100. What's 60 dB? 1,000. What's 80 dB? 10,000. So 40 dB is 100. So this straight line portion, which I can keep on drawing like this, is 100 over s. Now, but then it doesn't continue on like this. It gets to here, and then my straight line portion that I drew with. So you should draw this, with a ruler and a colored pencil or whatever to make sure you know what's going on here. So this then flattens out, and it flattens out up to about this point here where it starts to break down. So what would cause this to turn like this? Huh? Well, to get this to go up like this, you need to do what? You need to have a term that has what? That has a positive slope, because then a positive plus a negative will cancel each other out. So you need to cancel this out. So you cancel this out with something that looks like this. Well, what looks like that? Well, it's a tau s plus 1 term. Well, what's the tau? Well, the tau is this break point right here, because that's where it starts, right? That's where it starts. So tau is equal to, or 1 over tau is equal to what? 0.001. So tau is equal to what? 100. So 100 s plus 1 will then take you to this, and then you get to here, and you say, what happens? Well, now the slope changes, and it drops down here, minus 20 dB per decade. So what's going to give you a slope of minus 20 dB per decade? K over tau S plus 1. So K is 1 because you don't want to be moving these things up and down. So K for all of these is 1 because you don't want to move this up and down, but you want to change the slope. So now you have 1 over what? What's tau? Well, this tau is this one like this. So this looks like it's about 10 to the first, which is 10. And 1 over tau is 1/10. So it's 0.1 S plus 1. And then you get to take to this point right here, and it looks like it breaks down again. And what is 1 over tau here? Well, if you go down like this, you'll see this tau is what? 10 to the third, which is 1,000. 1 over 1,000 is 0.001. So this is 1 over 0.001 S plus 1. Now, how do you relate this to the phase? Well, the phase you can't do asymptotically. So what we do is we draw these boxes. So in other words, the integrator starts at minus 90 and stays at minus 90. At this break point, what's going to happen is that a first order term is going to go to plus 90. So minus 90 plus 90 takes you to 0. And then it'll stay at 0 until what? Until this break point, which will take you what? To minus 45. Excuse me. This break point will take you to minus 45, which is this point right here. So in other words, you can see that you can see what happens here. These break points are at the middle of these steps that or at least in the middle of these curved portions that show you how the phase changes. So in other words, so here the phase of an integrator is minus 90. But when you add this, you're going to add 90 degrees of phase, a phase margin. So it's going to go to 0. So this is between here and here, you got to go from minus 90 to 90. Then the phase starts changing gradually back down. So at this point here, at the break point, you get 45 degrees of phase lag, so this becomes minus 45. And then what happens is, over this portion here, this will eventually get to minus 90. So in other words, so again, asymptotically it gets to here, which would be minus 90. But you can also see that we have a break point right here because when you look at the actual phase diagram, if I look at K over tau S plus 1, and I look at the magnitude plot, so the magnitude plot looks like this. So if this is K, it's flat out to here and then breaks down. The actual plot looks like this. The actual plot looks like, so it bends down like this and then it hugs this parallel. If you look at the phase angle plot though, that plot looks like this. So this point here is 1 over tau, and this point here is 1 over tau. And so what's the phase angle plot look like? Well, if this is minus 45 degrees, and this is minus 90 degrees, it goes to minus 45 here gradually. So the phase so whereas this is K and then breaks down, this changes gradually. It doesn't stay like this and then come down. It changes gradually. So it goes through like this and then it changes gradually like that. So that's why when we look at the phase angle plot here, you have to look at as it's changing gradually because of this. Before this break point, it's already increasing in phase. And then it'll get up to, depending on how much frequency this spans, it may get up to 0 degrees. And then it's going to go down back to minus 90, and then it's going to go back down to minus 180. So you can tell that this is correct because what? An integrator has minus 90 degrees of phase lag. A first order term in the numerator will give you 90 degrees of phase, positive phase, so that gets you back up to 0. This will give you 90 degrees of phase lag. This will give you 90 degrees of phase lag. So now you're back down here at minus 180, and you better be there at 180, otherwise you got something wrong. So that's how you can tell if you're actually captured all of the break points, because let's say you missed that second break point. Let's say you drew a line that maybe looked like this. You thought this was a straight line, something like that. Well, you know right away you were wrong because that would only get you to minus what? Minus 90, minus, that would only get you to, yeah, minus 90. You need another one to get you to minus 180. So the phase angle can tell you how many breakpoints you actually need. So this is just using really an integrator and a first order term in the numerator or denominator and nothing else to approximate a complicated transfer function. So what then does the transfer function look like? The transfer function would look like what? So if you said, what are you going to type into MATLAB to then compare to the plot? Well, your transfer function equals what? It equals 100 over S, right? Times what? Times 1 over 100 S plus 1. Oh no, I'm sorry, that's not right. It equals 100 over S times what? 100 S plus 1 times 1 over 0.1 S plus 1 times 1 over 0.0001 S plus 1. So there's your transfer function. And if you want to write this, so you would write this as 10 or 100 times 100 S plus 1 divided by S times 0.1 S plus 1 times 0.001 S plus 1. So if you multiply all that out and you put that into MATLAB and ask for the Bodie plot, it will look exactly like that. It's right on the money. Okay? Yeah.
What if the magnitude diagram is not as nice as that and it goes like up and down?
What do you mean up and down? That goes up and down. What do you mean not as nice as that?
Like what if there's like an arc in the middle instead of just going down straight?
Well, I mean, second order terms look like this. So you know a second order term. So a k over s squared plus 2 zeta omega ns plus omega n squared. The Bodie plot for that looks like this. So here's omega. So what does the magnitude look like? The magnitude looks like this. It's still in k, and this is now. We would say this is omega n, and so what does the plot look like? Well, it's flat out to here, and whether it peaks up like this and then rolls off, or it doesn't roll off at all, depends on zeta. So whatever zeta is will either cause this to peak and then roll off, or just roll off. And this is minus 40 dB per decade. And then the phase angle plot is actually quite simple. So this is minus 90 degrees, and this is minus 180 degrees. And the phase angle at omega n is exactly minus 90 degrees. So the phase angle looks like this. It starts at 0, goes to minus 90 at omega n, then goes to minus 180 in the limit. And the magnitude plot depends on zeta. And so do these. Depending on zeta, there's a whole family of plots. In other words, the plots could look like this, or like this. So there's a whole family of plots. But they all go through omega n at minus 90 degrees. They all go through that. But you can see how the shape of the magnitude plot and then the phase angle plot will contribute to this. So that's a little messier. But you never need to use more than first order terms, second order terms, or integrators and differentiators to do an approximate Bodie plot. You never have to do that. You can always make any highly complex system appear to be essentially a combination of these simple terms. You just got to be a little creative. And of course, you just double check it in MATLAB. Just take your transfer function, get the Bodie plot and see if it looks like what you started with. In this case, it looks exactly like you started with. Okay? Any questions on this one? Okay, this we gotta talk about, talk about, that, let's do the root locus one. Okay, so let's say we have a transfer function. What's this transfer function? Okay, so let's say we have a transfer function that looks like this. So the transfer function is, we'll say it's equal to, so k over, we'll say, s plus 10, s plus 20, s plus 80, okay? And so this is GCG. So this is the open loop transfer function. And so we want to draw the root locus of this. So the root locus, by definition, is a plot of the what? Of the closed loop poles, right? The closed loop poles, because it's the closed loop poles that tell you what the transient response will be. Okay, so what does the root locus plot for this particular open loop transfer function look like? Well, the way we draw the root locus plot is you have your imaginary axis and you have your real axis, so real and imaginary. And so the first thing we do in drawing a root locus plot, we're verifying that the plot is correct. I'm not doing this plot, I'm doing this one here. Is to do what? Is to, there's some simple rules for drawing root locus plots. We don't use them to hand draw root locus plots anymore. We use them to check that the MATLAB plots are correct. So the first one says, first of all, how many poles do we have? Well, we have, in this case, we have 3 poles, right? And we have no zeros, meaning you don't have any terms in the numerator, but you got 3 poles in the denominator. So these are open loop poles. And so you start by plotting your open loop poles. So you got one here at minus 20. We'll say that's minus 10. We'll say this is minus 20. And then you got one over here, we'll say this is minus 80. So you plot your closed loop poles. And so then what do you do? Well, now, so if you looked at 1 plus GCG equals 0, we assume unity feedback. If you then solve this equation as k varies from 0 to infinity. So in other words, so now you let k vary from what? From 0 to infinity. So as k varies, so when k is equal to 0, you just have these plots right here, these points right here. So when k is equal to 0, you just have your open loop poles. As you increase k, what's going to happen? Well, you're going to have 3 branches. So the number of branches is equal to the number of open loop poles. So how many branches of the root loci? It's the number of open loop poles. There you have 3 poles, here I have 3 poles. Then the real axis portions, and if you just look at my notes, the SISO tool notes, I have all of this all laid out, which has a video that accompanied it, which you should have watched. So the real axis portions of the root loci, there's a rule that says the real axis portions are to the left of an odd number of poles and zeros. So you start from the right and you work left. You say, okay, there's a pole or a 0. So there's a root locus portion to the left of it. Then here's 2. There's nothing to the left of it. 3. Then there's a root locus portion to the left of that. So your real axis portions are here and here. So then we say what? Starting and terminating points of the root loci. So the root loci start at the poles and either go to a 0 or go to infinity. So the root locus plots start at the poles, and then they go to a 0, but we don't have any zeros, or they go to infinity. So what happens here, if you looked at the root locus plot in MATLAB, is that, so one pole is gonna go this way, another pole is gonna go this way, then at some point they're gonna meet, and then one branch is gonna go this way, and another branch is gonna go this way, and this branch is just gonna keep on going to the left. So these are the paths of the closed loop poles as k varies from 0 to infinity. So let's say you let k be some number, let's say it's 10, and maybe your closed loop poles were then here, here, and let's say over here. So those are your 3 closed loop poles. You don't care about this because the transient response for this is a very fast exponential decay. So essentially what you have now is a dominant second order system. And you can then treat it as a second order system where that's omega n, and this angle theta, the sine of that angle theta is your damping ratio, and it becomes a second order system. Okay. So to answer these questions, so where does it start? It starts at the open loop poles, and they go to a 0 or they go up to infinity. And so these branches go off to infinity, but how do they go off to infinity? Well, so there's going to be a point here, which would be the center of the asymptotes. And so you can see that this goes like this goes like this, and this goes that way. So there's a point here, so these branches go off to infinity at definite angles. This, and this go off at definite angles. And you can see that this angle is going to be 60 degrees, and this angle is going to be, for this one, is going to be 180, and this angle is going to be what, 300? Well, how do you get that? Well, the angle requirement is, and again, it's in the notes, it says it's equal to 1 plus 2k times 180 degrees divided by n minus m. So n minus m is the number of poles minus the number of zeros. So n minus m is equal to 3. Number of poles minus the number of zeros. 3 poles, no zeros. So if you let k equals 0, you get 180 divided by 3, so you get 60 degrees. If you let k equal 1, you get 3 times 180 divided by 3, you get 180 degrees. If you let k equal 2, you get 2 times 2 is 4, plus 1 is 5. 5 times 180 is what? 40. It's 900. 900 divided by 3 is 300. So you get you get those directions like that. And if you want to know where this intercept is, which is the real axis intercept of the asymptotes, that formula is the summation of the poles minus the summation of the zeros over n minus m. So we already know what n minus m is. It's 3. But what are the sum of the poles? Minus 10, minus 20, minus 80. So that's minus 110 over 3. So what's minus 110 over 3? I don't know. What's minus 35 something? Yeah, minus 36. Yeah, probably minus 36. Yeah. So in other words, this would be minus 36, which looks about right because that's minus 20, that's minus 10, minus 80. So these asymptotes would start here and go plus 60, 180, 300. So why do we have these rules? Well, we have these rules not to do the hand plotting, just to check to make sure that the Bode plot from the MATLAB is correct. Because you don't want to, you can't just trust your computer output without having something to check. You know, number of branches, for example. Asymptotes, where does it go asymptotically? So these rules are not meant for you to draw the root locus by hand, but meant for you to look at, to check to make sure the computer program isn't giving you garbage. Okay, so we go back now. Okay. All right. The root locus plot that we had looked like this. So our root locus plot looked like this. We had a pole, we had a pole, we had a pole. So these two came together. One went like this, one went like this, and one went to the left. So if I change k, so for example, let's say just for example, let's say k was 10, and for k equal 10, I had a closed loop pole there, the closed loop pole there, the closed loop pole there. Okay, and you would say, well, that's a stable system because this has a very quick decay. But this represents what? This represents what? A gradually decaying sine wave, right? And you know that this distance here is omega n, and the sine of that angle theta is equal to zeta. Okay? Now, what happens if you let k be, let's say k is 100? Well, then these poles will move. Let's say this pole goes here, this pole goes here, this pole moves farther to the right. So when you have poles on the imaginary axis, what do you have? What do you call that condition?
Marginal stability.
Marginal stability, right? Because there you have a sine wave that neither grows nor decays. So that's marginal stability. And then if they go up into the right half plane, you know you're unstable. So you have to have your poles in the left half plane. Here's the right half plane, here's the left half plane. So when you have the poles on this point here, on the imaginary axis, you have what we call marginal stability. Now, and so how close I am to getting to marginal stability in terms of a factor of safety, I can't really determine from the root locus plot. You know, there's nothing that tells me how much I can increase k before I get to this point, or before I cross over. So it could be I could just increase k by 1 or 1,000. I don't know, but there's no real margin safety factor that I can get from the root locus plot that will tell me how close I am to having marginal stability. And so we have to resort to the Bode plot to do that. And so the way the Bode plot works is, as we said before, so your closed loop transfer function is GCG, right, over 1 plus GCGH. And if 1 plus GCGH equals 0, we have marginal stability. And we know what that looks like from the root locus plot, marginal stability. So that means GCGH equals -1, but that means it has a magnitude equal to 1 and a phase angle of minus 180 degrees, right? Because when you plot -1, you plot it right here, so there's 1, -1, has a magnitude of 1, and a phase angle of either plus 180 or minus 180. And usually we call it minus 180. So when the magnitude of GCGH, which is your open loop transfer function, when the magnitude is 1, and at the same time the phase angle is minus 180, you have marginal stability. So what is gain margin and phase margin? Gain margin and phase margin are measures of how far you are from marginal stability. So in words, gain margin is the factor by which you could increase the gain to get marginal stability, nothing else being changed. Phase margin is the amount of phase lag you can add to your system, nothing else being changed, that will cause the system to go to be marginally stable. So these are your safety factors, and they're very easy to determine from a Bode plot, as we'll see. So here's the open loop Bode plot. It says the open loop Bodhi plot is shown, it's a closed loop system. Is the closed loop system absolutely stable? Unfortunately, I don't have a, oh yeah, I do, I have a picture of that. Yeah. Okay, so here's your Bodhi plot. Now, so this is the open loop Bodhi plot. You never draw the closed loop Bodhi plot because we use the open loop Bodhi plot to design the controller for the closed loop Bodhi plot. So if you're taking that control design course, you'll learn all about this, but we don't have all that time to go into depth in this. But in terms of gain margins, so what you do is you say, okay, here's 0 dB, right? 0 dB. If I go over here to 0 dB, where does it cross 0 dB? Right here. And then if you go down, so then if you go down at this frequency, you look and see what the phase is. Well, the phase is this, which looks like it's about what? Maybe it's minus 110 degrees, yes? So the difference between that and minus 180, that's your phase margin. Meaning that you can, 180 minus 110 is about 70. So you have 70 degrees of phase margin. If you added 70 degrees of phase lag, then this point would go here, which means you've got minus 180 at 0 dB marginal stability. So your phase margin is what this is here, in terms of, this is the additional phase lag that you can tolerate before you're at this point, 0 dB minus 180. So that's your phase margin. So now you go over here and you say, okay, where does this cross minus 180? Right here. So then I go up, I draw my dashed line up like this, at minus 180. Well, the magnitude is not 0 dB, because this is 0 dB, right? This is 0 dB. That's 0 dB. So what's the difference between 0 dB and this? So that distance is what we call gain margin, meaning that this is how much gain that you can tolerate before this is at 0 dB when the phase is minus 180. So this is minus 180 degrees right here. When this is minus 180, you can see the gain is less than 0 dB. So you're stable. But what's the gain margin? This is the additional gain you can have that would cause this point to then be at 0 dB. If it's at 0 dB at minus 180, marginal stability. So that's your gain margin and phase margin. And that's how you determine it from a Bodhi plot. It's as simple as that. But you have to do it on a Bodhi plot because in a root locus plot I can't quantify that. Because you have to understand, where does this come from? So and you can't think of equations. You have to think, what makes the closed loop system go unstable? In words.
Time delay and too much gain.
Well, more specifically, it's the imbalance between strength of corrective action and system dynamic lags. It's not too much of one or the other. It's an imbalance that causes it to go unstable. So you can't have the phase angle and the gain has to be in balance for a system to be absolutely stable. So phase margin is the amount of additional phase lag that you can tolerate, nothing else being changed, that you can tolerate before the system will be marginally stable. Gain margin is the amount of additional gain that you can tolerate, nothing else being changed that would cause the system to be marginally stable. So they're factors of safety. You can't, it's not one or the other, it's both. You have to have good gain margin and good phase margin, and they have to be substantial. They can't be marginal themselves, because marginal systems on paper work only on paper. They'll never work when you build them. Never, never, ever. So phase margin and gain margin have to be substantial for your system to work in hardware. So that's gain margin and phase margin. It's as simple as that. And you get that from an open loop Bode plot. I sort of enhance this a little bit, so you can make I'll let you do this yourself. It's just matching, 1, 2, 3, 4, A, B, C, D. You gotta do the matching.
Wait, question.
Yes.
Did you say you changed?
No, I just made X's and O's.
Oh, okay.
You couldn't see the X's and O's on the actual. I posted the improved version, but in the actual version, you couldn't see. You had to look closely for the X's and O's, and even in this, you got to look closely for this to see what the numbers are. But even you can tell, you can do the matching without knowing magnitudes of numbers. So, but if you have any questions, just come see me, and I'll try to get a clearer printout for you. This one. Okay. What time do we have?
8:22.
That's all it is? Is
That's all
8:20?
it is.
That's all it is 8:22?
Yeah.
Yeah.
We got time for this.
I got time for this?
We got time for this.
Okay. I need a drink first. Okay. So a Bode plot is, so you would put a sine wave, all right? At some frequency, sine omega t, and what you get, so A sine omega t, A-N, and you get A0 sine omega t plus phi. So you have an amplitude ratio, right, which is A out over AN, and we represent that usually in dBs, call it magnitude, and then you have the phase angle degrees, phase angle. Now, what we do with the Bode plot is we break this up into two plots, meaning we plot magnitude, right, dB versus frequency, and then we plot phase angle versus frequency. So we have amplitude ratio and phase angle, and we make this into two plots: magnitude versus frequency, phase angle versus frequency. But there's another way to plot this information, and the way to plot it, the result is called the Nyquist diagram. And so again, I have A in sine omega t, and what I get out is A out sine omega t plus phi. And so instead of plotting this on two sets of axes, what I can do is I can have what is called a polar plot, meaning that I can plot magnitude versus, God bless you, versus phase with frequency implicit. Now what does that mean? Well, so what I have here is a ratio of A out over A in, and that's some number, that's a magnitude. And then I have associated with that is I have a phase angle. And omega is is implicit. So how would I create a polar plot? Well, I would just have a set of axes, and so let's say I have so at some frequency, we'll say omega 1, I have a certain magnitude and I have a certain phase angle. So let's say, this point is omega 1. The magnitude of this line is A0 over A1, and this is my phase angle. So this is my phase angle, and this is my magnitude at that frequency. So at some frequency, which would correspond to, let's say, in my Bodie plot, if I picked a frequency, I would get a dB, I would get a certain data, and at same frequency, so let's say omega 1, I would get a phase angle. So at omega 1, I would have a phase angle, and I would have a magnitude. So rather than plotting two plots, at omega 1, which is implicit, at omega 1, I have a certain magnitude, which I plot as a length of line from the origin to that point, and the phase angle is measured counterclockwise from the positive real axis. So then let's say I have another frequency, omega 2. Then how do I know what the plot of this is? At omega 2, maybe I have this magnitude, and then I have this phase angle. So that would be magnitude and phase. So what you do is for each frequency, you plot magnitude and phase. And whereas the Bodie plot separates out magnitude and phase with frequency explicit, here you substitute in a certain frequency, and then you measure A0 over AN and the phase angle, and you plot it in a polar plot, meaning magnitude and phase. And you do this for 100, 1,000, 1,000,000 frequencies, whatever you want. Well, MATLAB does that for you. And this polar plot that I just illustrated here is called the Nyquist diagram, after Henry Nyquist. And so what does a polar plot look like? Well, a typical polar plot will look like this. So, for example, we don't want to look at this one. Let's look at, so a typical polar plot would look like, well, we would use MATLAB to do this for us, but let's say we had let's say we had our transfer function. So our open loop transfer function looks like K over, well, the one that we were using, S plus 10, S plus 20, and S plus 80. So what does the Nyquist plot of this look like? I mean, you could actually draw the Bodie plot by hand yourself, because you know what S plus 10 looks like, and then S plus 20 and S plus 80, and they just sort of, add to each other. But what does the Nyquist plot look like for this, the polar plot? So I want to look at what is the polar plot for this look like, which is another name for the Nyquist plot. Why don't we just, I don't know exactly what that looks like. I mean, I have an idea, but let's just go to MATLAB and see what that looks like. So I'm just going to go over here and get MATLAB up on the screen and type this in, and we'll look at the plots. And we'll look at it in the SISO tool. Okay, so let's get out of this. Let's open up MATLAB. So I got, what is S plus 10, S plus 20, and S plus 80?
Yeah.
So, okay, so if I want to, if I want to multiply two things together, so if I want to multiply, let's see, S plus 10, S plus 80, right? 1 plus 80, and what's S plus 10, S plus 20? That's S squared, 10, 20, plus 40S, plus 10 times 20, plus 200, right? Yeah. Good. So if I want to multiply those two, that's what I get. So my transfer function, so my plant equals, parentheses, 1 in the numerator, and then 1, 120, 3,400, 16,000. So there's my, whoops. Oh, I forgot transfer function, sorry. The transfer function. Theta. So there's my transfer function. And just to check, to make sure I did this right, roots of 120, 3,400, 16,000. What are the roots of that? Whoops, we made a mistake. What happened? What's S plus, what is it, 10 and 20?
S plus 10, S plus 20, and S plus 8.
10 and 20, so it's S squared plus, so it's S squared, oh, I'm sorry, this should be, where's the convolution? Convolution. It should be, it's S, 10 and 20?
Yeah.
So it's, oh, it should be 30, right? And then 10 and 200, it should be 30, sorry. So, convolution, so it's, it should be 30. It's 10S plus 20S, that's 30. And then plant, that's, so that should be what? This should be, 110. That should be 2,600. 1,600. So that's my plant. And then where do I want the roots to be? Roots of what? Roots of what? 110. 2,600.